So some introductions. I'm Richard. I'm a developer. I mostly focus back-end, but I'm interested in everything. So I want to know about you guys. Who here is a developer or writes code, either as a hobby or as a profession? Okay. What about just little scripts? Okay. Is anyone QA or product or non-developers? All right. So who here knows what a CPU is? CPU, central processing unit. Okay. And who knows what memory is? Okay. That's talk. So we're going to talk about two different things. We're going to talk about memory access and something called cache appearance. Hopefully they'll make sense. Feel free to ask me a question at any point in time. I might go too fast, I might go too slow, just let me know. Okay, so what is mechanical sympathy? Ultimately, it's sympathy to the machine. Has anyone read Do Androids Dream of Electric Sheep? Tough crowd. See Blade Runner?
Yeah.
Okay. Electric sheep. You feed it, you take care of it, no one will really know that it's not an electric sheep. That's sympathy. Your car, if you're sympathetic to it, it'll last you a long time. Your servers, if you're sympathetic to them, they'll do really cool stuff for you. And they won't go down, and they won't give you phone calls at 3 a.m. So mechanical sympathy was kind of coined by F1 driver Jackie Stewart. I forget the year, but he was award-winning and accomplished. And his quote to some effect was, you don't have to be an engineer to drive a car, you just have to have sympathy for it. You really have to understand and take care of it. I don't drive, so I don't know, but change the oil, use the correct type of gas. If it's a manual, make sure you're changing gears at the right time, so on and so forth. And in software, it was championed by someone named Martin Thompson. Take a look at his stuff, his articles, his blogs, his videos. It's all awesome. He really championed it. So I want to start by clearing up some myths. So mechanical sympathy, you might be thinking, that might be premature optimization. It is not. Largely, it's writing code in a way for your computer that it really is able to take full advantage of the hardware. As opposed to premature optimization, which really much would be, I think it's going to behave this way, therefore I'm going to make this change and realize it's not true. And we'll go over some examples of how we can be sympathetic without premature optimization. So the other myth is that high-level languages aren't suited for performance-sensitive systems. Not true. Another myth, and I hear it all the time, and I want to bring it up because we'll see it a little bit later, and because I'm using Java kind of as a primary focus of this talk. Java is not slow, and it's certainly not always slower than C. You'll see some examples in a bit. And finally, high-performance code and clean code are exclusive sets. That kind of goes back to that premature optimization. If you write optimized code, it's probably going to suck. If you write very clean code that targets your domain very specifically in a way that is as fast for your domain as possible, it's probably going to do pretty well. So let's talk about memory. So in this screen, we have two processors, processor 1, processor 2. And in each processor, we have 4 cores. 1, 2, 3, 4. Every core has a cache, or a series of caches. And we'll, in this case, call them level 1, level 2. And somewhere outside, we have a level 3. Each cache, level 1, is small. It's fast. It's incredibly fast. It's about the fastest you can get from registers. Basically, it's where data gets stored in the processor while it's running. The level 2, it's a bit slower, it's a bit bigger. So the L1 cache might be 32 kilobytes, your L2 cache might be 512 kilobytes. Then finally, you've got your level 3 cache. Level 3 cache is usually bigger. Most modern Intel processors now are 8 megabytes. It used to be small, but it's fast. And then finally, we have memory. And memory is that common point where all the data in your system that's running right now is live. The data flow is kind of bidirectional in each case. Each processor talks and writes to L3, reads and writes to L1 and to L2, and then the processors talk to each other, usually through some sort of something called an interconnect. In Intel terms, it's a quick path interconnect. Does that make sense so far? Okay. So I'm not lying too much. This is a die mapping of a modern Haswell Intel core. You can see our processor. You can see there's 4 cores. There's the L3 cache that all of those cores share. And then here's the L2 cache, and here's the L1 cache. So that's basically what you're writing code against. So how does memory get from memory to your processor to do its operations? Well, basically, the processor says, I need data. And it'll go out and say, I need this specific data. It'll check its L1 cache first to see if it's there. And if your application just started up, it'll say, I don't know about this data, I have to go find it in L2. Processor will go check L2, the level 2 cache, and say, is my data in here? And it'll probably say no, because your application just started up. It might stop there, because you might only have 2 caches on your CPU. You might have 3, and it'll go to 3. It'll say, I don't know, and you go to memory. And then when you go to memory, data gets transferred back down to the L3, L2, L1 cache in lines. And the lines in the majority of modern processors are 64 bytes. So every time you go get memory, you get 64 bytes of memory back based around the address that you requested. Does that make sense? Okay. So before I go on, there's some information that you probably want to know. Search for this chart online. Use it, reference it, consult it. It'll really help you go from what Ernest and Dimitri were discussing before. How long does a packet take to go from California to the Netherlands back to California? Well, in this case, 150 milliseconds. How long does data take going between, well, off a solid-state disk? On average, 150,000 nanoseconds. So consult this. You won't find it every day. It's something you're dealing with, but it's a constant reminder of how fast things can possibly go. Now, before I go on, you might ask, this is web performance, we're not writing C. That's okay. At the end of the day, everything we're writing needs to work well, and it needs to work well maintainably, and it needs to work well scalably, that everyone can understand. So everything that I'm speaking about today can be applied to anything and everything. The smaller your data, theoretically the faster it can go, and I'll go on more about that later. So, like any company, Kijiji writes a lot of particle fountains. It's in our business logic. When you post an ad, we generate particle fountains and a lot, but it's a good way of demonstrating how things work. So that particle fountain was generated more or less by this algorithm. And you can look, we have a particle has an x coordinate, a y coordinate, a z coordinate, and a velocity for x, y, z. And ultimately, gravity dies. It's negative 9.8 meters per second, and it gets modified by velocity y. It's not perfectly physical, but it's close enough. When the particle itself bounces or leaves the screen, or stops, we just reset it to 0 and blow it up again. And then finally, if it hits the ceiling or if it hits the floor, we inverse the actual velocity and take 50% off the actual speed. And that gives us a nice particle fountain just like that. They come up, they fall down, they bounce, they go back. Okay. So, how do we model this in code? One way, if you're familiar with object-oriented programming, we create a particle. We have an x, a y, a z, we have a velocity x, y, z, and we're going to use doubles just because they're more fun. And we have, I counted correctly, there's somewhere in the range of 550 million of these particles. So we're going to have an array of 500, ultimately ended up being 512 kilobytes of data. And then every single one we're going to instantiate and say the x coordinate of this particle is set to, or let me restart here. If the x position is 0, we're going to add the velocity of x, and we'll have an x coordinate of x plus 10, whatever the velocity is. So, does this code make sense so far? Okay. So what does this look like in memory? Here's our array of particles. Particle array, particle array, particle, 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 particle. Now, in Java and the majority of object-oriented programming, these are references or pointers. They point to the actual data sitting in memory. And I know pointers scare people, but at the end of the day, it's really just this arrow. The pointer says the object starts here. These are object headers. It's a bit of the data that just Java uses to say it's an object, where it is, how it's used. X, Y, Z, dx, dy, dz. That's pretty much it. Does that make sense so far? Okay. If it doesn't, let me know. Now, why is this red arrow here? This is a cache line. This is 8 bytes, effectively, let's call it 8 bytes of data. That's going to be transferred from memory into your processor. I have an interesting note about fragmentation, and I think it will become clear later. We'll have to see. If it doesn't, let me know. When we're using Java or any garbage collected language, which includes JavaScript, which includes .NET VMs, which includes almost anything garbage collected, we're going to get fragmentation. And that just means the memory you're reading in is not right after each other. You're going to say, I have a particle here, and a particle over here, and a particle over here, but there's nothing particle-ish in between. So, as an example, simulate fragmentation, create a new particle, put in some garbage, create a new particle, put in some garbage, and now we've got non-contiguous particles. So what does that look like? It looks like this. We have a regular particle array again, it's nicely contiguous, but then we've got the end of a particle here, some garbage, another particle. So, the second way that we can implement this particle business logic is using a bunch of arrays. So we can have one array for the x-coordinates, one array for the velocity x-coordinates, one for the y, dy, so on and so forth. And again, to update the state of the particle, we just add the velocity of the ith index. Then we have x0, x plus vxi becomes x25, whatever x ends up being. Does that make sense? So what's that look like in memory? It looks like this. And it's not necessarily stacked this way, it's just a big long array, but we've got x, we've got y, we've got z, and they're all in different places in memory. Next way we can implement it is one big long double array. Theoretically, this is almost the same as using a two-dimensional array, which is kind of like this one too, somewhere in between. So in this case, what we're going to do is going to look kind of like that object one, where we're saying, well, the 0th position of the index, or the double array is x, the I plus 1 is xv, velocity of x, then y, velocity of y, so on and so forth. And what does that look like in memory? It's like this. So similar to that array, except now there is no pointer array, it's really just x, y, z, x, y, z, x, y, z, 550 million times. So, we go back to the picture. What made this explosion? A very trivial algorithm. We're going to do 10 iterations, and every iteration we're going to do 20 seconds of simulation, of updates. And we're just going to update the fountain. And update means we take the x, the y, the z, add the velocity to it, re-render it, do it again, as fast as we can for 20 seconds. Write the counter, how many times we've done it, every 20 seconds, and then finally print the update, the number, and we'll plot it and have a bunch of fun. So, I'm going to back up here. Again. Let's hypothesize. What do we think is going to happen when we're rendering this? Is it going to be fast? Is it going to be slow? There's no right or wrong answer. We're trying to sympathize with the machine. Sympathy isn't always the correct science. We'll get it wrong, we try again, we'll get it wrong, we'll try it again, we'll keep getting it wrong. Until we eventually get it right. So how is this going to work? How do we think? How many particles are we going to display? Billions, millions? Let me give you a hint, it's in the tens of thousands range. So somewhere between 1,000 and 100,000. Gut feeling. Let's go with 50. And how about this one? Why do we think, or what do we think about this one? Is it going to be as fast? Is it going to be faster, slower? Okay. And this one. Faster, slower, 50, 70, 100,000, 10,000?
Slower.
Okay. And this one. What shows this one? All right, let's find out. So I just ran this through in my head and plotted it out. So number one right here, and 50 wasn't too far off. It was a good median when we factor in these two. We've got almost 80,000 updates in a 20-second period for the single array Java implementation. So that was that last one, and I heard someone say it was the fastest. Absolutely. What actually came next is I compiled this also in C, and the algorithm I changed a little tiny bit to be more C-ish. Again, trying to get the best out of C I possibly could. And I turned on, oops, that's supposed to be optimization 3. I turned on as much optimization as I could. To be fair, that Java is also going to optimize when it's executed. So this came in at a pretty nice constant, somewhere near 78,000, 80,000, some spiked a little bit. And then we've got the object array, the very first example. And it's coming in pretty close. I mean, we're looking at 72, 75,000 throughout the life. It's not that far off. And then we've got that multi-array, not quite as good as a Java array, so we're still making pretty good hypotheses here. And we've got that fragmented seed. It's this bright orange line down here. It's coming in around the 20,000 mark, not very fast, not very good. And then for fun, I also compiled this in Node.js. So I believe it's Google's V8 engine. And it came in somewhere around the 19,000, 18,000, 20,000 mark of updates per second. So do these results make sense so far? And I'll explain why in a bit, I hope. So that single double array, sorry to call it that, but that's what it is, it produced the most updates. And we're talking order of magnitude compared to the slowest. The contiguous particle actually was running at 8.6% fewer updates, but if you stop and think about it, that's still really fast compared to some of the other implementations that we just saw. And it kind of goes against intuition that a lot of people say objects are slow, but there's a couple things that we've done. One, for example, is we allocated those contiguously. So every time memory was being accessed for that particle, it knew about the other particles, and I'll explain that in a minute. The other thing that happened was that everything was almost as compact as when we were actually doing with this single double array. The data was almost always in the same place compared to this. The fragmented particle array was just way off, and I hope it will make sense in the next slide when I explain why. I hope you go home understanding this part. And just to completely outcast that rumor, this Java implementation did work faster than the optimized C. Interesting caveat, if we bump up the number of particles, that story floats around. Okay. So why did this single double array outstrip all of the other implementations? Really, it's about prefetching for the most part. Prefetching is when I'm talking to memory, I know what's next, or I can hypothesize as a processor what is next, and I can go get that information before I need it. Striding effectively just says, I've looked at index 1, and then I looked at index 2. I can now hypothesize that I'm going to look at 3, 4, 5, 6, through to 50 million. It's going to keep happening, and you'll probably continue to be right until you're done, or until you're not right. So as you're operating on that first double, or that first array, or that first cache line of doubles, we're going to fetch the second one, so that when you're done that first piece of work, that second piece is running right away. So again, if we go back and look at how that layout for the objects works, it's a little bit weird, because now there's even more information sitting between, and we're dealing with two arrays, an array of pointers, an array of memory, or a block of memory holding all the objects. But again, striding the prefetching kicked in and said, every time I bring in this cache line, I'm looking at the next one next. Therefore, I should always bring in both cache lines at the same time so that the data is always there. And it ends up being that we only have an 8%, 9% difference in implementation. The fragmented particle just was crap. And if you look at what happened, there was almost 18 times more cache misses. And if you remember from the beginning, a cache miss is when the processor says, I want information, I want it right now, but I can't find it, it has to go to memory. And if you go back to that table, that means not half a nanosecond, not 7 nanoseconds, not 12 nanoseconds, but 100 nanoseconds. That's a long time compared to half a nanosecond. So the more times you have to go up to memory, because your code is fragmented, your code isn't necessarily being sympathetic to your hardware, you got a long way to go, and things are going to suffer. So does that make sense so far? So that's all single-threaded. So if you're Java developers, or sorry, JavaScript developers, this is 100% always completely applicable. You're dealing with objects slightly more so than anything, so it's going to hurt a little bit, but be friendly to your machine and it will reward you. So now we're going to go into more of a multi-threaded land, where actually the inverse of that juxtaposed or cohesive, sitting beside each other, I can't come up with any more adverbs or adjectives for this. That data sitting beside each other actually becomes a detriment instead of a performance gain. So we have the level 1 cache, we have the level 2 cache, we have the level 3 cache, we may even have the level 4 cache. Sure, there's hardware out there that has 5 levels of caches, who knows how many. And it's got to be all kept in sync. So how do we keep level 1, level 2, level 3 all in sync, all the level 1s of all the cores? How do we do that? And it's a coherence protocol. The most popular is called the MESI protocol. You'll also see it as MSI, MESIF, MOSI, so on and so forth, every derivative thereof. So what does it mean? every cache line is marked, and it's not marking as in we're checking off with a marker. It's marked as in somehow this cache line is being identified as I'm either modified, I'm exclusive, I'm shared, or invalid. How that happens is implementation specific. Probably not too important to know exactly how it's doing it. But at the end of the day, a cache line is modified, which means somebody changed it, and you got to go find out who and what changed it. You've got exclusive, meaning I own this cache line, you guys don't, so if you want it, you have to tell me. Shared means everyone's reading it, it's happy, it's probably never changed data, not bad. Invalid means it's wrong, throw it away, go get it from memory. So the question becomes then, we've left this land of single thread, we're in 2 threads now. What if 2 threads have a variable each on the same cache line? And in the single threaded model, that was optimal. That was every single time you read the one cache line, you probably had more data on the same cache line, so you could prefetch. Well, now the problem's flipped. 2 threads are trying to modify the same cache line at the same time for completely different purposes. And that's no longer a benefit. This is called false sharing. And it's basically an interesting way of saying that 2 threads are sharing the same thing, but by accident or by implementation details. So what does it look like? Say we have a work counter. And for every thread, we're counting the number of things that are done for the work counter. And because we like global state sometimes, we have an array of work counters that are shared between all the threads. Good implementation, why not? But let's say it was the best one we came up with this time. So we have 2 work counters, they're instantiated, it's got a long done, forget about volatile. Let me just say that for the sake of this talk, volatile is just going to mean that anyone in the world can read the state of this counter at any point in time. It's there for semantic correctness, but forget about it for the time being. So, the algorithm. As the thread's working, I'm going to keep updating the counter. For this implementation detail, that's all it's doing. It's counting 50, I think the implementation I did was 55 billion times. It didn't do work, it just counted. So what does this look like in memory? We've got an array of work counters. It's too long, but because I was lazy, I didn't change my graphics on 20 work counters. And every work counter has, again, this is Java implementation specific, C#, and the entire CRL is probably the same. The object has a header and the counter value. Another object, let's say we implement these continuously, they're all stuck in the same page in memory, or same line in memory, so they're all sitting the same way as those doubles were in our first implementation. So that's going to be very contended. That's false shared. So this counter right here is falsely shared with this counter right here, because they're not being modified by the same thread. They're completely different things. So how do we fix this? Tag it. Put in a bunch of padding. If you're familiar with C or C++, this might make a lot of sense. You're going to say, I just want a bunch of stuff after my counter so that it pushes the next counter onto the other page line. Or we could have done what we did in the first example, was throwing a bunch of garbage in between every instantiation. Maybe that works, maybe not. Try it, measure, always measure, don't assume. What's interesting though is that in just-in-time language like Java or any of the .NET languages, it's tricky. You're implementing against unspecified behavior. You don't know if what you're going to do is correct. So again, you have to try. And in this case, you're in the land of unspecified behavior. So you're going to be smart, but you might get burned by it. The last thing that's important is even if you're not in just-in-time, all hardware is different. Sometimes your cache line is 128 bytes. Sometimes your cache line is, I don't know, maybe smaller. But the point is, if you make an assumption, you could be wrong, so always test it on your target hardware and environment. So what does that padding look like? Well, here's our padded work counter, the number of tasks done, and a bunch of padding that's not important. So if we run this, what do we get? So we've got our padded implementation in orange, and we've got our unpadded in green. What is this showing? The number of threads that are executed. So in this implementation, we have 1 thread, 2 threads, 4 threads, 8, 16, 32. And the number of time that it took to execute this task, which was for each thread, 64 threads, spinning through 50 million counters, or 5 billion counters. So as you might expect, every time we increase the number of threads, we almost decrease our actual execution time by half. So with 1 thread, we were 160 seconds. With 2 threads, we were 80 seconds, 4, so on and so forth. So one interesting caveat here, the 60 and 32 are identical performance. This is again knowing your hardware. This was executed on an 8 dual socket 8-core machine with hyperthreading. And the problem with hyperthreading is that even though it looks like you have 2 processors or 2 cores per physical core, you don't. It's actually using a bunch of tricks to say that as I'm fetching memory, which again, it's 100 nanoseconds, it's really slow, I can do another operation. So it's going to start doing 2 operations when it looks like, well, it's going to do 2 when you think, whatever. Anyways, the point is, because our implementation was simply updating a counter, there was never any free time. So the hyperthreading made absolutely no difference between 16 and 32 runnables. Now the interesting part, the unpadded implementation, it's tending in the same rough direction, half each time, till some point here. Now, why 8? I don't have an answer for you. If you look at literature or if you look at examples online, the majority of the tipping point on modern hardware is approximately 8 threads when things just go crazy. I'm sure there's smarter people that can answer this. I can't. So Google, you'll probably find an answer. So the padding, or the unpadded implementation, is good until you're running 8 threads. Then all of a sudden, you're actually going slower than when you originally started with 1 thread. So ultimately, having 2 pieces of data on the same line in a multi-threaded universe is not as beneficial as having 2 pieces of data on the same line in a single-threaded universe. And that is all I have.